The question comes from ACE Physics Syllabus Code 9702-21. This is May, June 2016. Question reads, a ball of mass 150 grams is at rest on a horizontal floor as shown in figure 3.1. We are to calculate the magnitude of the normal contact force from the floor acting on the ball. All right. So remember that an object with mass and a gravity field has a force called weight. Weight equals mg. And the normal contact force is that force which sort of balances out weight for an object sitting on a solid surface, right? It acts normal or perpendicular to the surface. If all there was the weight, then the ball would accelerate in that direction because it's made of, solid particles, and so is the floor. It can't just like push those out of its way like we can push air out of our way or water out of our way, some fluids, right? So the solids are just that, solid. So the normal force here is going to equal the weight, and they've given us enough information, and we know enough about physics, G, to calculate the normal force here. So it's going to be weight equals mg. Now they want the unit Newton of force. Okay, is a Newton a gram meter per second squared? Everyone in class is shaking their heads no. They know that it's kilogram meters per second squared. And so the mass of 150 grams is 0.15 kilos. That is a necessary conversion in order to get newtons of force. Going back to that learning objective about newtons will relate derived units to base units. Derived unit, but it's equal to what base units? Kilogram meters per second squared. The only way to get newtons of force is to multiply kilograms times meters per second squared. So that's the acceleration due to gravity, that's the mass in kilograms, and our product is both equal to the weight and the normal force, right? Now, just a moment ago, we talked about Newton's third law force pairs. You get 1.47 newtons for this, about 1.5 newtons. We talked about Newton's third law force pairs. Here we have two forces, which are indeed equal in magnitude and opposite in direction. And yet they are not a Newton's third law force pair. These forces are not a Newton's third law force pair because they act on the same object, for one, and Newton's third law force pairs are always between two different objects. And they are not forces, we say, of the same type. Okay? This is, as they mentioned, a contact force. So there's a force of the floor on the ball, and there's a force of the ball on the floor. That's the Newton's third law force pair. Here, we really only care about the force that the floor is exerting on the ball. We don't really care that there's this, and usually the symbols that we would use to care about it would be like this. The normal force prime, like this is the third law force pair that while the floor exerts a normal force on the ball also exerts an equal and opposite force down on the floor. That's the third law force pair. But we don't really care about the floor in this problem, right? That's a force acting on the floor. All we care about is the ball. So we tend to not really care about the Newton's third law force pair. Hey, what's the force pair for this weight? There's got to be a force pair for that. So if the Earth is pulling down on the ball, somewhere down here is a giant Earth. Okay, and the ball pulls up on the Earth a little bit, just like we saw in the example of the boulder crashing. Like, you sit in your chair and you kind of feel like the normal force of the chair pushing back up on you. You have weight that's acting down, but your mass also pulls up on the Earth a little bit. Okay, and that's the third law force pair. And so if there's weight acting down, let me sort of zoom out here. Here's the Earth. Here's this, floor here. And so this ball has weight acting down, but the whole Earth is being pulled up by a little bit. Okay, weight acting down. There's the Earth. Equal and opposite force acting up. That's the third law force. But beyond, really, we need to use this question. This is explain your working. I'll leave it to you to kind of go through how we're able to arrive at this answer. Again, it has to do with knowing that the weight and the normal force are going to have the same magnitude, but they act in opposite directions. And again, let me just emphasize or reiterate, just because two forces are equal in magnitude and opposite in direction does not automatically make them Newton's third law force pairs. They must be of the same type, like they're either both contact forces, they're both gravitational forces, and they must act on two different objects for it to be a Newton's third law force field. It says the ball is now lifted above the floor and dropped so that it falls vertically, as illustrated in figure 3.2. Just before contact with the floor, the ball has a velocity of 6.2 meters per second downwards. The ball bounces from the floor and its velocity just after losing contact with the floor is 2.5 meters per second downwards. The ball is in contact with the floor for 0.12 seconds. It tells us so. Lift the ball up, we drop it, it's going 6.2 meters per second just before it hits the ground, and then just after it leaves the floor, it's only going this fast. If you've already had a chance to go through the slides and you learned about perfectly elastic collisions and the linked video, the relative speed of approach equals the relative speed of separation, we can automatically look at these velocities and go, this is not a perfectly elastic collision. If it were, if all the kinetic energy were conserved, there's no change in mass, so this thing would have to bounce up with the same energy, with the same velocity. And the fact that it doesn't, we know, okay, well, it's not a perfectly elastic collision, but it is a collision, right? It's colliding with the floor. We can just look at the velocities and say, well, it's not a perfectly elastic collision, it's some form of elastic collision. Most collisions are. The question goes on to ask us, state Newton's second law of motion. State Newton's second law of motion. Now, Newton's second law of motion is most commonly thought as F equals mx, or a body of constant mass. So we have to qualify it, I think, for an object with constant mass, force is proportional to acceleration, or the quantities force, mass, and acceleration are related by this equation. Those are good ways to think about the second law. Force is the rate of change of momentum. If we think about force as being equal to the rate of change of momentum, and we know that momentum, the change of momentum is the final minus the initial, and we know that momentum is mass times velocity, we can kind of think about this as m minus mu over the change in time. And if the mass is indeed constant, we can factor it out. V minus u over t is acceleration. So this better statement, the way we define force, the rate of change of momentum, really does become F equals ma when mass is constant. Right? Because V minus u over t is a. Right? So we have F equals ma. Right? That term there is a minus u over t. But mass isn't always constant. Sometimes it's changing. Can anybody think of an example when mass changes? For our example here, the mass of this ball doesn't change, right? So we kind of just use F equals ma, right? When mass is constant, it simplifies down to, that. But can anybody think of a case where, like, the mass of an object that's, experiencing a force changes? I can think of two examples, and you could probably think of a lot more once I maybe give you these examples. So rocket science, my favorite, okay, continuous variable mass. We need calculus to really deal with that, all right? And we'll do some rocket science later on in the year. But because the mass is always changing, right? We have exhaust gases, right? So the mass is decreasing, as we mentioned earlier. We get a little bit of the rocket in space, we leave most of the rocket behind. So it's always changing its mass, right? So that's the situation. Variable mass, we really need like momentum to make better sense of it. Another one that sometimes students, if you give them long enough, usually students will come with like a snowball rolling down a hill, right? It's going to pick up snow as it kind of rolls down the hill, so it's going to increase its mass, right? So here's an example of decreasing its mass as a function of time, as a function of engine firing, and a snowball rolling down a hill would increase its mass, as a function of time as it picks up snow, roll down the hill. So we calculate the average resultant force on the ball when it's in contact with the floor. Well, let's try to use Newton's second law here, this form of it. I'm going to maybe use that equals if we have to. We want the average resultant force. So we have force equals the rate of change of momentum. And because we do have constant mass, I suppose we could just factor that out, but let's see it like this. mv minus mu over delta t. It gives us the final velocity as 2.5 up, okay? The initial velocity just before the collision was 6.2 down. We got to decide which direction we want to make positive. I'll call down positive because that was the initial direction of motion. So here it was moving with a mass, and again, you could factor out m here if you know if that was your preference. So it's got a mass of 0.15. It's got a final velocity of negative 2.5 meters per second. Again, I'm assigning direction up to negative because it was initially falling down. Okay. And I just prefer to call the direction of motion initially positive. You can make this positive as long as you keep track of it. Okay, as long as you keep track of which vector is close to the other one, it really doesn't make a difference. And we'll show that. Minus 0.15 kilograms of mass times initial velocity now is positive 6.2. And they told us that that happened over a time of 0.12 seconds. So note that we're going to get units of kilogram meters per second in the numerator, right? When we subtract these two quantities, we're getting just units of momentum. Right? You can only subtract momentum from momentum. So kilogram meters per second in the numerator divided by seconds in the denominator, kilogram meters per second, or kilogram meters per second squared, which are indeed units. So I get negative 0.375 0.93 over 0.12. 0.93 plus 0.75 is negative 1.305. 2. I get calculator value negative 10.875 newtons. Now, the magnitude of the force, remember, we don't really care about the negative sign anymore. The magnitude is just how much. It tells us which way. Force is a vector. The sign convention tells us the direction of the force. And we've decided to call up negative. So it tells us the direction by assigning up negative, right? This is the velocity that it left the floor with. That tells us the direction that the force is exerting on the ball. It should kind of make sense to you too that if a ball is falling down and then it bounces up, which direction floor exert a force on it in? Well, it's got to be the direction it's going to like make it direction. If there is somehow a force on it in the same direction it was moving, it would go faster in that direction. The only way to stop something is to exert a force on it in the opposite direction it's moving. To turn it around. The magnitude of the force is 11 newtons, and the direction of the force is 11 newtons up. Now it says, state and explain whether linear momentum is observed during the collision of the ball with the floor. And here, if you sort of naively do a calculation of equals mv 0.15 kilograms times 6.2 meters per second. And then you compare that with 0.15 kilograms times 2.5 meters per second as an attempt to disprove the fundamental law of physics that a moment ago I told you there is no violation or exception to, then you need to kind of rethink this, right? If your strategy is, oh, I will show here today how, physics from this day forward will be, known in this new light, okay? You should probably rethink it. You're in high school physics, or, everything is very well established, and you say that with grad school, pretty great discoveries. What we have to do is realize that, of course, linear momentum is conserved. How do we then account for those losses? Where's the rest of the momentum? I mean, there's no lying about that number. It is slower than this. So yes, the momentum of the ball is less than it was here. That's true. But forces always exist between what? Two objects. Always two objects. What's the other object? The floor. Okay, and because it's like immovable, we tend to forget about it. But all the rest of that missing momentum is in the floor. Okay, the atoms that make up the floor are shaking. Okay, and all that momentum we'd be able to account for. Let's actually take a look at what the language of Marx maybe says for this one here, and see if you know, how would you kind of put that into your words? State and explain whether linear momentum is conserved. Yes, linear momentum is conserved during the collision of the ball with the floor, and you can kind of give you a clue there. And you can quantify, you can say the apparent, you know, missing, or the apparent missing momentum would actually